Welcome to The Explainer. Today, we're going to demystify that massive hidden infrastructure that literally powers our modern world. If you've ever driven past an industrial site, a power plant, or even a really large commercial facility, you've definitely seen them. Those absolute giants of industry just sitting quietly in the background, doing the heavy lifting of thermal management. Okay, let's dive right into this. I know you've looked at these mysterious cloud-belching monoliths and wondered, what exactly is going on in there? Are they making clouds? Are they polluting? How do they actually work? Well, today we're breaking down the anatomy and physiology of cooling towers to understand the engineering marvels hiding in plain sight. Here's our quick roadmap for today. We'll cover the industrial workhorse, the math of efficiency, cross-flow versus counterflow, the visible plume myth, and finally, the smart tower revolution. All right, part 1, the industrial workhorse. So according to the SPX Fundamentals Guide, the main gig of these towers is rejecting process heat right into the atmosphere. But the deeper purpose here, it's actually conservation. By efficiently recooling and reusing water, instead of constantly pulling fresh water from our natural reservoirs and then dumping scalding hot water back into local estuaries, these towers are absolutely vital to global environmental conservation. They protect aquatic life from crazy temperature swings while literally saving millions of gallons of water. Moving right along to part 2, the math of efficiency. Now, when we talk about cooling tower thermodynamics, range and approach are the two absolute key concepts you need to know. Range is simply the temperature drop. It's the difference between the hot water coming into the tower and the cold water leaving it. But the approach, well, that's the gap between that cold water output and the ambient wet bulb temperature of the outside air. To put it simply, the approach is your ultimate indicator of performance. In a perfect, mathematically ideal world, your cold water temperature would exactly match the wet bulb temperature of the outside air. That is simply the lowest temperature achievable solely by evaporating water. But in reality, achieving that 100% efficiency would require an infinitely large tower, and it would cause massive water evaporation losses. It's practically impossible. So the real-world goal, the sweet spot engineers aim for, is hitting a practical efficiency of about 70 to 75%. That's where the math actually meets industrial reality. Okay, section 3, crossflow versus counterflow. It's a bit of a heavyweight bout here. On one side, we've got the crossflow tower, where air travels horizontally across the falling water using just 2 air inlets. On the other side, the counterflow tower, where air travels straight upward, fighting directly against the falling water using 4 air inlets. Now, if you're in a dense urban area and your heat load is under 750 tons, counterflow is going to be your champion because it saves vital footprint space. But as we'll see, crossflow brings some incredible versatility to the table, especially with unpredictable environments and maintenance. Let's look at how the water actually moves. With a crossflow gravity basin, the water gets pumped up exactly once, and gravity does the rest of the work feeding the nozzles. It's this open, super easy to access space where a maintenance worker can literally just stand up inside. Meanwhile, the counterflow design uses a pressurized header box to shove water through branch arms and nozzles. It's highly effective for sure, but the working space inside for maintenance is incredibly cramped and pretty complicated. So why does the structural difference actually matter to the folks operating these machines? Well, it comes down to varying flows in cold weather. Cross-flow towers are incredibly flexible. Thanks to their specific nozzle cups, they can drop down to just 30% of their design flow and still distribute water evenly. That keeps the heat load pushed to the exposed outer edges, which totally prevents freezing. Counterflow systems, though, they get into real trouble if you push them below 70% capacity. The water loses pressure, and you get what's called channeling. The water basically just clumps together, leading to completely unpredictable cooling performance and, dangerously, hidden ice buildup inside the tower during winter. Which brings us to section 4, the visible plume myth. I want to state this as forcefully as I possibly can. That thick white cloud you see billowing out of the top of a cooling tower, it is not smoke, it is not pollution, it is quite literally just warm, moisture-laden air that is condensing as it meets the cooler outside air. That water vapor was already present in the atmosphere. The evaporative process just made it visible to the human eye. From a direct carbon and emission standpoint, it is completely harmless. So here is the crucial point. When companies are pressured into hiding that plume just for visual reasons, a process called plume abatement, they accidentally create a massive, ironic energy penalty. To stop the condensation, they have to install hybrid dry sections just to actively reheat the exhaust air. This requires bigger fan motors, way more electricity, a larger physical footprint, and a ton more steel. Basically, by suppressing a harmless water plume just to look green to the neighbors, you actively ruin the pure efficiency of evaporative cooling and increase the system's actual carbon footprint. All right, final part. Section 5, the Smart Tower Revolution. I absolutely love this analogy from the mock cooling source material. For decades, these towers were run on manual programmable logic controllers, or PLCs. Operators actually had to walk out to the physical towers to make adjustments. But running these highly engineered systems manually today, it is exactly like driving a race car in first gear. You'll get to the finish line eventually, sure, but you are leaving an immense amount of performance, optimization, and efficiency right on the table. Let's see how IoT integration builds a modern intelligent system. Step 1. Smart sensors constantly collect real-time data: temperature, vibration, water flow, the whole shebang. Step 2. Communication networks instantly beam this data away from the site. Step 3. Cloud or edge computing analyzes the data for historical trends. And step 4, the system takes automated action. It adjusts fan speeds, tweaks pump output, and adapts to the daily weather, all without a single human having to step foot on site. It enables true predictive maintenance. And the return on investment here isn't just theoretical. According to a case study on IoT integration, implementing these smart, adaptive controls yielded a massive 15% reduction in total energy consumption. On top of that, facilities saw 20% fewer emergency repairs. Why? Because the sensors were catching vibration anomalies and tiny bits of wear and tear long before the equipment actually failed. This is precision engineering meeting modern data science. Which brings us to our final thought. When we look at the pure math of cooling tower efficiency, the physical realities of crossflow versus counterflow, the massive energy penalty of trying to hide a harmless water plume, and the brilliant energy savings of IoT controls, we really have to ask ourselves a question. Are we optimizing our industrial infrastructure for true, measurable sustainability, or are we sometimes just engineering for the optics? It's a pretty fascinating lens to view our modern world through. Thank you so much for joining me for this explainer. I hope you never look at a cooling tower the same way again.